Okay, so on this here, this was before we talked about what affects enzymes and so on, so you get to do some interpretation of the graph here. And so the two enzymes were pepsin and lipase, and then it asked you to read up here in this Y box some background information, and it asks you which body organ is pepsin active, and you should have the stomach. Remember we talked about that since then when we did notes on Monday, that the stomach has those special cells that secrete acid that makes it a very acidic environment, and that provides the right environment for the stomach enzymes to work properly. So then B, when it says in which body organism is pancreatic lipase active, the name is misleading. It's called pancreatic lipase, but it's not active in the pancreas. It's active in the small intestine. They call it pancreatic lipase because it's made in the pancreas and then gets secreted into the small intestine where digestion actually happens. There's actually no food that ever enters the pancreas, so the pancreas for the digestion produces enzymes. All right, so then when we look over to the next page, you should have pepsin most active at 1.5, lipase at 8. Then it asks you for 4 and 5 to compare pepsin at the rate of reaction at 1.5 with lipase at 1.5. So instead of, let me just put this up here so we see it. And so what we have here, here is pepsin and here is lipase. So at 1.5, pepsin is very active, and at 1.5, when we look at lipase, it goes down to 0 at pH of 4. So anything less than a pH of 4, there's no rate of reaction. I do want to point out that notice with the pH, as you go above or below the optimal pH range, the rate of reaction goes down. So notice it doesn't go to 0 right away. So I wanted to point that out about, when we talk about enzymes beginning to denature, when they're fully denatured, you're going to have a rate of reaction of 0. But in the process of losing its shape, it can still be active a little bit. So the rate of reaction goes down until it's fully denatured at, in this case for lipase, at a pH of 4 or a pH of 12. And so yesterday in the toothpick example, I had on average about 3 groups do having denatured enzymes, and I had some groups go, well, wouldn't it just be a rate of reaction of 0? And it would be if it's fully denatured, but if it's not fully denatured, you might have still a rate of reaction. It's just a slower rate of reaction. Okay, so I had some people change the shape of the enzyme. Some people did your hands with the enzymes and cross their fingers and tried to do it. And I had some people change the fingers that they used to change it. So they used the pinky, all right, and the ring finger to try and break it. So that's a change of the active site. So therefore, they saw that the reaction rate slowed down. I had one group in another hour want to just try to take their thumb and just use their thumb and smash. So because they were like, oh, well, if it totally unravels, it's just like a flat hand. So you know what I mean, and try to do that. So I had different people do different things, but I just wanted to point out that in the process of denaturing, you may get some rate of reaction like this. Okay. And then in some cases, when it's fully denatured, you get a rate of reaction of 0. And so, for lipase, it doesn't work at all in that 1.5. So then number 5 asked you about a pH of 8. So on the flip side, lipase is optimally working at a pH of 8, and your pepsin isn't working at all. It's out of its pH range. Anything 5 and above, the enzyme is fully denatured, so you don't get any rate of reaction. So then number 6.
When you get a chance, come see me.
Sorry.
I'm sorry, I just trying to find her.
It's okay. So number 6 is pulling in information from chapter 5, what we know about the shape of enzymes. So it's asking about the enzyme structure and why it is that the enzyme is going to be denatured as you either become more acidic or become more basic from that optimum pH. And so I have drawn basic enzymes like this, showing you the active site has a specific shape. But remember, enzymes are proteins. Proteins are chains of amino acids that have a three-dimensional shape. So you have this three-dimensional shape due to this chain of amino acids. So can somebody tell me what it is about changing the pH, either making it more acidic or more basic? What's happening to the three-dimensional structure to cause that to happen? Like, what could a change in pH do? Thinking about start with this. What's the ultimate reason why the protein has a three-dimensional shape to begin with? Why does the protein have a three-dimensional shape to begin with? What's going on there? Elizabeth?
Isn't the R groups are like bonding to each other?
That's right. All right, the R groups are bonding with each other. So like when you have curves like this, the reason why this has a three-dimensional shape the way it does is because there's an amino acid here and amino acid here. Those R groups are interacting with one another, and they can form like hydrogen bonds and things like that. And so that's what's holding the shape together. So now let's add one more piece of this. So now if we change the pH, how is that going to screw up the shape? How's the pH going to mess up that shape? What is pH? When we change the pH, what are you really changing? Grayson?
You change the hydrogen.
Yeah, remember pH is hydrogen ions compared to hydroxide ions. And so as the concentration of hydrogen ions goes up, what happens to the pH? I'm going to go to the left or the right here. To the left, it becomes more acidic, which means the pH goes down. So if you have a higher concentration, let's say, of hydrogen ions, do you see that these H pluses, they have a positive charge? They may be attracted to some of these R groups and be attracted to them and interfere with the R groups interacting with each other because they're interacting with the H pluses. And so therefore, when you change the concentration of H pluses and OH negatives, that can interfere with the R groups, and if they interfere with the R groups bonding, guess what? The shape is going to get screwed up, all right? The shape is going to change, and if we change the shape, eventually we change the function. And the shape here that's really important is that active site shape, okay? And so we're going to run out of time here, so we'll stop here and we'll go over the rest of this. Tomorrow, finish up whatever you didn't finish up with your toothpick ace activity.